Hello again, welcome back to the Electronics channel. Tonight we've got another device on the bench for repair. This one is a dareaudio.com V1100 Power Amplifier. It came to me with the lid already removed, some screws missing. Looks like there's a wire disconnected and there's some fuses missing in the power supply section. So I'm going to guess that something's gone bang further down the line, so we're going to need to find out what it is. First thing, I think we'll bring you in, have a closer look around the inside of this. It's got a pretty impressive looking transformer inside it, so I guess this thing is probably 1100 watts rated output. So yeah, let's get you inside. So here's what it looks like from the front. We have gain control for channel A, we've got a clip light for channel A, protect, I guess that's a bridge light, a power light, similar for the other side. Except we've got a light for, I guess that's parallel mode. That normally means joining the two inputs together so the channels run effectively in mono. Another protect light and the clip light for channel B as well. Moving inside, we've got this big toroidal transformer. You can see there's a good hefty lump there. I think that accounts for most of the weight of this thing, which is about 20 odd kilos. Let's see if we can see a specification on that anywhere. You can clearly see 64064 and a 022 for the secondaries, and then a 240 for the primary. There's no rating that gives a hint about the VA, but I'm going to guess it's probably about 1000 VA, maybe 1200. Quite a sizable transformer. And it comes into the power supply board here. The yellow is the 22 volts auxiliary stuff. You see a little bridge rectifier and capacitor and maybe a regulator there. And then we've got the main inputs from transformer. So the blue wires come out to the bridge rectifier, come back here. This is the wire that's left disconnected. Looks like it's supposed to go on down here. There's a fuse missing that side. Looks like that's the way the bridge rectifier connects to the capacitor bank there. See the fuses in line with this cable. Just about see the PCB traces there. This side we've got similar arrangement. Again, fuse missing. So we've got 3 caps of 6800 microfarads, 100 volts per rail. Presume a split rail. And we've got some fan-cooled heatsink tunnels, one for each channel. We've got 5 devices on each side of the heatsink. Let's see if we can see what these are. C3519A, is that? This is a nice looking Sanken transistor specifically designed for audio applications. So we've got 180 volts, 15 amps, with a 50 megahertz bandwidth, 130 watts dissipation. And looking at the safe operating area, it looks very good. So even at 100 volts collected to emitter, it can still do 1 amp, so that's 100 watts of dissipation. Below that voltage it's actually more. So yeah, it looks like a very good rugged transistor for audio applications. And we can also see from the gain versus collector current curve there that it maintains its gain very linearly with current right up until about 5 or 6 amps, and since we've got 5 of these in parallel, that's up to about 25 amps worth of current, where the gain's actually rising as the current increases, so it's going to have no problems driving the output whatsoever. Nice transistors. I presume they're complementary on the other side. Bunch of 0.5 ohm emitter resistors. Wow, 0.5 ohms. That is a generous value. Well, that's going to pretty much guarantee good current sharing anyway. So then we've got all the rest of the stuff. We've got some output relays here and here. Got some front end stuff, I'm guessing. Maybe the balanced to single-ended converter op-amps. Maybe these ones, I'm not sure. Another set of op-amps. So maybe this parent design is based on an op-amp at its heart, who knows. It's 4558 op-amp there. And the input one, what does that say? 5532. It's a classic. Good. So let's have a look at the back of this thing. So So around the back of the unit we've got our mains inlet, suggesting a fuse of 15 amps. Seems a bit optimistic for an IEC, but there we go. We've got combined Nutric and 4mm outputs, XLR and quarter-inch jack in, and then we've got input sensitivity control, limiter on off, ground lift, and then amp mode, parallel, stereo or bridged. All fairly standard for this kind of stuff. So for the front panel you can see the gain potentiometer, got the LEDs just mounted on the board, multi-way cable for in and out, another gain potentiometer, and you see the power supply PCB from a different angle. See we've got two NTC surge reducers in line there. Don't know if they're in series or parallel. Looking like the tracking suggests they're in parallel, I think. Never really quite understand why they put NTCs in parallel. You know, you'd think that they would share the load, but intrinsically, as they get hotter, their resistance decreases. So the one that's hotter will be hogging more current. So, I don't know, seems to me like actually one of them would take the brunt of the load and the other one would be pretty much redundant. But anyway, you quite often see more than one in parallel like this, so I guess there must be some logic to it somewhere. If anyone knows the answer to that, let me know. It looks like there's a relay there to bypass those once the thing is started up. That's about all she wrote, I think, here. So let's get the multimeter out and see what we can see in terms of shorts on the power supply, shorts on the output stages, and anything else that looks interesting. Okay, the most important bit, have a drink of tea. Essential to any repair. Okay, so given the power supply fuses have been removed, that's between the rectifier and the capacitors. So first thing to do is check the power supply itself doesn't show a short circuit straight after those fuses. So it comes in on this terminal. These two terminals actually appear to be in parallel. There's only one wire. Go to this side of the fuse. So this side of the fuse is the power supply. So I'm going to go from there, which is a negative input, to ground, which I can see is labelled on here. Okay, momentary beep there while the caps start charging up. So there's no direct short to ground. We'll do the same for positive side. Again, comes in on this side of the fuse, goes out on this side. So I'm going to get a beep while the caps charge up. And again, no direct short on the positive rail. Let's try positive to minus just to see. Nothing there. Okay, and the output stages are still fully connected. It looks like the blue wire here is the negative output of the DC supply, and the red is positive. They're all still connected. So that will suggest that there's no short circuit from plus to minus. So maybe not a catastrophic failure, and there's no evidence of any smoke or anything blown up in here. So okay, let's continue the search. Next thing to check would be if any of the output power transistors are blown. One way we can do that is to connect to the common output bus. So that would be where all the emitter of all the power transistors come through their emitter resistors. That's these white things. They all join together on the common bus, and that's the output of the amplifier normally. We normally go through this small inductor here, and then there'll be a Zobel network as well somewhere, I would guess. But because there's a relay in the way, we can't simply connect to the speaker outputs. We've got to go before the relay. So I can see that all the emitter resistors common up on a big thick track that runs down here. So I'm going to put one probe on something that looks like it connects to that. So this resistor, for example. And then I'll try something else that's connected to the same track just to see if we're connected. And we are. So if we then go to the positive rail, which I can tap off over here with the fuse again. Open circuit. If we go to the negative rail, open circuit. Okay, so it doesn't look like we've got any blown power devices on this channel. That is, unless the emitter resistors have failed as well. Sometimes when the device blows, the emitter resistor fails, so we would then not measure anything, but let's take it that they're okay for the minute. Again, I'm going to do the same thing this side. I can see the emitter resistors all common together on a big thick track. I can see that that resistor couples onto that. I'll check another point just to make sure. Yep. Okay, positive rail. No shorts to there. Negative rail. No shorts to there. Okay, so the first signs are interesting. No blown power output devices, it would appear. So, given that's the case, normally at this point I think I will connect the bench supply up. The low voltage circuits, maybe the fan circuits and the protection circuits, probably run on the 22 volt AC winding of this transformer. So if we power that up, we should see the lights come on. Maybe the protect mode will stay on because there's no high voltage rails present. And then we can bring the high voltage rails up on the power supply, see if there's any excessive current draw, see if there's any DC offsets on the output, see if there's any weird stuff going on at all. So I think that's going to be the next stage. We'll try that. So I'm going to hook up the bench supply. I'll see you back in a minute. So if you've followed any of my other repairs, you'll know this is fairly standard procedure for me. I'll try and get the low voltage power supplies up, see if we can start applying a high voltage safely via a power supply to ensure that, you know, if there are any faults, we're not going to cause a high current and damage anything else. So I've applied the mains connection for the low voltage winding, so when we turn on we're going to get that low voltage output. So I just need to connect my power supply now. So I'm going to set this up for split rail, so same configuration like we've seen previously. The voltages of the two channels of the power supply track each other to give us a split supply. I connect the two center connections together, which gives me a common ground, and then I get a positive and a negative compared to that ground point. So I can see on this power supply here we've got a ground connection here which is unused, so I'm going to go on to that with my ground connection. My positive and minus connections, I'm going to go onto those fuse holders where we know they connect to the capacitors. So I think we've got positive this side, negative this side. Okay, so the power supply is connected. I've set a current limit of 0.5 amp on each rail. So the first thing I'm going to do is turn on the AC supply to get the low voltage stuff up, see what happens. So here we go. Okay, I've got two power on lights. The protect light came on to start with, but it's actually gone out. So I guess it's not seeing a fault because of the lack of high voltage. It's probably not monitoring that. It may be monitoring the output for DC offset over current conditions, over temperature conditions and so forth, but it may not actually be looking at the power supply rails themselves and going, they're within normal standards. You know, not all amplifiers do that. So we're now in a position where we can turn up the voltage here, see if there's any abnormal current flow. So let's turn on the power supply. Away we go. Let's charge these big capacitors up, see if anything strange is happening. So we're seeing 120 milliamps. Okay, so the current's getting quite high quite quickly here. So we're at 15 volts, we're already seeing 300 milliamps. That seems a little bit unusual. Yeah, and the higher we go, the more current we're seeing. So something definitely looks to be wrong there. So I think, just feel around, see if there's anything obviously warm at this point. Doesn't appear to be. Okay, so I'm going to monitor the output bus that we checked before, where the output of the amplifier should be present. I'm going to monitor that point for DC offset, see if there's anything going wrong with the channels there. So I'm going to go back up to, let's try 15 volts. Put my meter negative probe on ground, and I'm going to go onto the emitter bus here. The outlet here. It's got 54 millivolts on it, which is okay. Move on to the emitter bus over this side. That's got 62 millivolts on it. Also okay. And given that the protection is not kicking in, it may be that the amplifier is already up and running. Maybe they're just severely overbiased. Why both channels would be showing that, I can't explain right now. What I'm going to do is apply an input signal, connect some speakers up, and just see if it actually is any audio passing through, because that will give us some confidence that the channels are okay, substantially okay, and then we can work out why the current draw is higher than we expect. Okay, so I'm going to connect speakers up. I'm going to connect the signal source. So I'm going to use my MP3 player again. I'm going to adapt it to 1/4 inch jacks, which can go straight into that. We'll get that playing. We've got gain controls on the front, so they're on minimum. And then somewhere I have my new trick to 4mm adapters, which allow me to plug my hi-fi speakers in here. So I'm going to push the new trick in, but I'm not going to twist it closed just yet. Because you can use the new trick connector with the twist lock as a kind of a switch. So I'm going to bring the amplifier rails up again, 15 volts. Okay, still seeing that quite high 300 milliamps draw, and then I'm going to just tap the new trick on and off to see if the speaker reacts. No, nothing. Not a click, nothing. Slight click on this channel, but we saw a 50 odd millivolt offset, so that's probably to be expected. Okay, speakers are connected, source is playing. Let's turn up the controls a little bit. I can hear that there's a roughness to the control there, so it would look like there's no audio coming through, but it may be that there's just not enough supply voltage here for the input stage to be operating. They might be operating on some kind of resistor dropper from the high voltage rail, so sometimes those won't work when you're running at low voltage like I'm doing right now. Of course, I've just remembered there are 4mm sockets on the back of this thing, so I don't need my adapters. I can just plug my speakers directly in and connect the positives to make the switching. Okay, so I'm going to just probe the voltages on these op amps to see if they're anything like what we might expect. So I'm going to go from ground again. Let's go to the positive pin, assuming it's a dual op amp. Yeah, I've only got 1.2 volts there. Minus 0.9. Let's try the input stage one. Yeah, 1.2 minus 0.9, yeah. So there's simply not enough voltage to allow the input op amps to operate. So there are quite a few presets inside this amplifier. There's one here, 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 here and here. There's another one hiding away. No. So it's not going to be easy to see which one is the bias preset on this particular amplifier to start with. So I think what I'm going to have to do is either risk it and increase the voltage further. I'll have to increase my current limit to take account of how much current is being drawn. try and get it to the point where the op amps are operating, or find a way of powering the op amps independently, or dragging their rails up so at least they can operate normally, whilst we still have full control over the power amps power draw. So I think there are some large wire wound resistors rather flakily floating above the PCB here in a couple of places. I wonder, because it does appear like they connect directly to some Zener diodes, which are also sticking up here. There's two in series that have been soldered together. Can I see anything like that on this side? Yes, there's a couple more there. And it does look like that goes to the op amp power pin. So let's just have a look at that again. So again, meter probe negative on ground over here. Let's have a look. Yeah, you see on that Zener diode there we've got the 1.22 volts positive supply. That connects this resistor. Yeah. On the other side of that resistor we have the 15 volts. So it would appear to be a resistive dropper with a Zener stabilizer after it. Just check that that 1.22 is the positive supply. It is. Okay, so it's looking like it is a resistive dropper with Zeners to regulate the voltage running from the high voltage rail. So at the moment the op amps aren't powered sufficiently. So the way around that is to apply a second power supply to give us plus or minus, let's say 6 or 7 volts, just to get the op amps running. We connect that directly to the output of the resistive dropper, and then we can keep the voltage on the power amps low to protect them, whilst hopefully allowing the front end to work, and then hopefully we'll get some audio throughput. So let's give that a go. Okay, so now I've set up a second set of power supplies again to give me a split supply. These ones are independent, so they won't track each other, but I can set the voltages ahead of time and switch them on simultaneously. So again, I've got a common ground connection which I'm going to take back to the same ground point, plus and a minus output, which I'm going to find out where to connect those up shortly. Okay, so I'm going to connect this new ground center tap with a new pair of supplies to the same ground point here. I'm going to find out which end of these dropper resistors is the correct end. 16 volts on that end, and there's our -1. So we want to connect to this end, the -1, and then this end of these resistors, which is the positive. So we're going to connect positive, just move that out of the way, positive to there, negative to there, making sure we can't short anything else. Okay, speakers are disconnected at the moment, but let's bring up the two power supplies to, let's see, let's go for 8 volts. It's just drawing about 20 milliamps now, so that's fine. Okay, so we've got 8 volts on the op amps now. So let's see if the speakers work now. Still got just a tiny offset on there. Speakers reconnected. Source still playing, I hope. Yep. Try the gain controls again. Okay, we have some sound coming out of one channel. Very crackly pot. Nothing on the other channel right now though. Let's check these input op amps now. -8 on the negative terminal, +8 on the positive terminal. The output of this op amp is at 0 volts. that one is also 0. Zero there, so it would appear the input stage is now operating normally. These op amps here, part of the limiter circuit, because you can see this funny looking heat shrink tube here is most likely to be an LED here, looks like an LED, and an LDR. You quite often see that kind of configuration used in power amps as a limiter. So when the signal gets to the point where, excuse me, where the amplifier is clipping, the LED will be lit up, the LDR resistance drops, and that's fitted inside one of the gain control circuits. So maybe in the op amp feedback or something. So it's often used to regulate the gain when the amplifier is clipping, to stop it clipping severely. So it's quite a common arrangement of a LED and LDR used for that purpose. Sometimes see it called a Vactrol. But so far everything looks normal. There's just no signal coming out of one channel, so we need to trace the signal through the amplifier now to see where it's getting to. So to do that, I'm going to get the oscilloscope out and probe the signal. Okay, so I've got the oscilloscope connected now. I've got a single probe which I've grounded onto one of the speaker outlet grounds. It's all common back to the power supply ground, so that should be okay. We've got our MP3 player still playing music into our inputs at quite a high level. So the thing I can spot here is this pair of dual screened cables here are what go to the front panel potentiometers for the gain control. Now these are running in single-ended, they're not balanced. There's an input to the potentiometer, an output, and then a ground connection. So this will be after the input stage, balanced to unbalanced converters. So if we can see a signal on here, this header, then that should show that that first stage is receiving a signal from the MP3 player, okay. So let's go and have a look in here. This should be ground, so there's nothing showing there. Let's have a look at this. Yep, there we go, we can see the audio signal there. We're on 200 millivolts per division, so peaks of about 400 millivolts or so. And if we look on the red, that must be the output of the pot, because that's currently 0. If I turn this channel up, yeah, so we're seeing a small signal there. So the other channel, where turning the pot up does nothing, let's have a look at that. Well, again, the audio signal is present on the white wire, so that suggests the input stage is working. So look on the output of the potentiometer and turn the potentiometer up. Yeah, and there's the signal. Now I can faintly hear the audio. Just hear some high frequency stuff coming through there. So it seems like there's just going to be some kind of, I don't know, it sounds a bit like a bad connection or something, but I don't know. But anyway, the input stage is working, so we trace the signal all the way through to the potentiometers on the front and back to the board now. The next stage looks like, so let's just see if that's, is that where the pot comes back? Yes. So the potentiometer signal comes back to this resistor here, the other side of which looks like it goes to this LDR, the limiter. So let's just have a look on the other side of that resistor. Yeah, again the signal is still there, so that would appear to be passing through the limiter okay. It's not clamping that signal to ground. And we've got an electrolytic capacitor here. Resistor here, let's have a look on there, see if we can see the signal again. No, can't see it there, but then we're not really sure what we're probing here. Yeah, without a schematic it's going to be a bit tricky to trace this through, but we'll do our best. So looking at the channel that does work, there's a switch on the back to disable the limiter, isn't there? So maybe we should try switching that. It doesn't appear to be making any difference. Of course we haven't checked the mode switch either. So let's try the mode. Oh, okay. Oh, look at that. So it would look like, let's get you into the camera here. You can see this switch down here in the corner, which is the mode select switch. It's just a bit dodgy. Moving it around has actually cleared the problem. We're now getting sound on both channels. So just while we're here with the oscilloscope connected, I thought I'd just check the speaker outputs, see if there's any sign of any oscillation or anything funny going on there. So here's, you can see a little bit of DC offset when I connect the probe there. But there's the signal, looks good, no oscillation. Let's try the other channel. Again, signal there, no sign of any oscillation. Okay, great. So what we found there then is that the mode select switch on the back, the parallel stereo bridge mode switch, is just a bit dodgy, needs cleaning. So could it really be that's all that's wrong with this? I'm still a little bit concerned about the amount of current that's being drawn on the high voltage rails, even though we're only at 16 volts at the moment. I mean, the amplifier is clearly running because I can get sound out of both channels. But this channel is noticeably, it's not warm, but it's noticeably above ambient, whereas the other side is stone cold. So I wonder if the bias setting on this side has gone a bit AWOL. So I need to work out which potentiometer is the bias setting, see if we can adjust that. We can check what the bias is by looking across the emitter resistors, if I can figure out which points to probe. So I think we can do that right now actually. So let's see if we can measure the bias current on this slightly worn channel. So I'm going to measure the volts drop on one of the emitter resistors if I can. So I'm going to go to the emitter buzz bar here, which is the output of the amplifier, and I'm going to try and touch one of the transistor outputs there. So I can see a voltage of 16 or 17 millivolts across that 0.5 ohms. Let's compare that to the channel that's cold. I can just about get onto that pin there. So on the cold channel, I'm seeing 0. Okay, so it would appear that because we're running at very low voltage, there's not really any bias current in the channel that's cold. But on the other channel, which is just slightly warm, there's already a reasonable bias current flowing. So it's only about, what did we say, it was 17 millivolts into half an ohm. So it's about 30 odd milliamps, and that's per transistor, because we only measured across the one emitter resistor for one transistor. So that would total up to, what, 30, 60, 90, 120, 150. And since we're drawing about 170 milliamps from supply, I think the majority of that is probably going through the output devices in here, which are over biased. So we need to work out where the bias is set on this channel and see why it's not correct. We've already seen that it doesn't appear to be oscillating, which is one reason it could be drawing too much current. So there was a preset. There's a preset at the end here for this channel, and there's also one here. Now, I think the presets up here are probably going to be something to do with setting the limiter, maybe calibrating the limiter threshold, because they're near the limiter circuits, which consist of this op amp, surrounding parts, and this Vactrol device. However, there is 4 presets here. There's another one there as well. There's a lot of presets in this device. But I think the ones out on the limb on their own over here, at the ends of each amplifier stage, are looking more likely to be the ones of interest, I think. I think we're going to be fairly safe to try adjusting this I've got a photograph of the positions of the presets as they are set now. So I'm just going to try tweaking this one. See if, okay, yeah, that's immediately dropped the bias down massively, just with a small adjustment there. Yeah, okay, check we're still operating. It's having audio at the moment. Okay, channel's still operating normally, so with the bias cranked all the way down, it's not the limit of travel for the potentiometer, but the current's dropped to quite a low value now, 40 milliamps. So I'm going to try increasing the voltages I'm applying now. So we're at 16 at the moment, go to 20, up to 30. I'm still drawing only 60 milliamps, so that looks good. Interestingly, the current drawn on the other rails is beginning to drop, the op-amp rails that we're powering separately, because now of course the dropper resistors are contributing more current to running the op-amps, so the current required from the power supply is dropping accordingly. So we'll keep going, 30 up to 40 volts now, and we're seeing 70 milliamps, 50 volts, plus or minus 50 volts. Let's check the bias on the channel which we think is good and okay from a bias point of view. So I'm going to drop back in on that same transistor because it's about the only one I can reach easily. Looks like I'm seeing 0 on this channel. So let's see if this bias control for this other channel is still affecting the current draw. It is. So actually the preset does appear to be working as intended. Let's try adjusting one of the other channel. Yeah, that too is increasing the bias current, as you would expect. So let's give it a little bit of current and let's see whether we can now see a volt drop on that resistor. Yeah, there we go. 8 milliamps, sorry, 8 millivolts on that half ohm, so 16 milliamps in that transistor now. So we are able to adjust and set the bias on each channel, and it would appear both channels are working fine. So we've got some crackly pots, we've got some switches that need cleaning. So it looks like it's going to be a case of just cleaning it up, checking that all these presets are actually okay. Yeah, so I think that's going to be all there is to this one. Cleaning it up, putting the fuses back in, replacing those. It looks like the bias for this channel has gone out of control at some point, maybe due to the preset being faulty or badly adjusted. And that's maybe taken out the fuses, or it's constantly overheating and they've just given up the amplifier and, you know, said it's not worth repairing. So in the next part of the video I will clean up the switches, potentiometers, check the presets are all working okay, and we'll go about checking the output of the amplifier is clean and stable and is all okay, and then that'll be it. So yeah, that's all for this part 1. We'll see you in the next part. Bye bye for now.